Hello APChem, this is Mr. Coker and this is chapter 12. We're going to do the first three sections this week and it's called Chemical Kinetics. So start reading on page 467 and watch this video and we'll be working on some kinetics problems in class. Kinetics is the study of chemical reaction rates. For example, if you want to work in industry and make chemicals, you would be very interested in how fast the chemicals can be produced, the rate of the chemical reaction. A classic example of this is the industrial production of ammonia by the Haber process. You can make the argument that the Haber process is the most important reaction of the 20th century. Without ammonia, you can't grow the amount of corn and other crops that are needed to support the high level of population that of people that has grown in the 20th century. And so ammonia, the production of ammonia industrially really has avoided the starvation of the people on the planet. So you could argue that that was a very important chemical reaction. If you want to do some reading, read up on the Haber process. It's very interesting politically and historically, just exactly how the production of ammonia was, the process was developed. Kinetics then is the study of the rates of chemical reactions. It's best illustrated with an example. So for our example, let's take a look at the reaction, the decomposition of nitrogen dioxide to nitrogen monoxide and oxygen. 2NO2 gas makes 2NO gas plus O2 gas. Now we could define the rate three different ways. We have a reactant and two different products, so we could look at any of the three things as a way of defining the rate. We could look at the rate of the disappearance of nitrogen dioxide. We could look at the rate of the formation of nitrogen monoxide, or we could look at the rate of formation of oxygen. Which one you look at basically depends on which one can be easily measured in the laboratory. Typically for rate, we want to define the rate to be the change in the concentration of these chemicals over the change in time. The rate can be an average rate. You can take two different times and measure the change in the concentration and divide by the amount of time elapsed. Or if you'd like to define the instantaneous rate, you can plot the concentration versus time. Excuse me. You can plot the concentration versus time, and by drawing the tangent to the curve, the slope of that tangent would be the change in the concentration over time at that given point. So what we're looking at here at the bottom is the decomposition of nitrogen oxide at 300 degrees Celsius. The concentration is plotted versus time. So we could say that the rate is the negative change in the concentration of NO2 over the change in time. That would be the rate of consumption or disappearance of NO2. That would be equal to the rate at which NO appears over time, or the change in the concentration of NO over the change in time. 2 times the concentration of O2 over the change in time would be needed to define the rate with O2, because O2 forms at half the rate that NO appears. So if we want these all to be defining the rate the same way, then that would be how we would have to compare the rate found in with the different chemicals. So you can see on the graph that the rate can be found by taking the tangent and taking the slope of that tangent, because that would be the change in the concentration over the change in time. You can tell that NO2 is falling at the same rate that NO is rising, but O2 is rising at half the rate that NO is rising. You can tell that these are not linear, that they are curved. Mainly that's because the rate depends on concentration, so the rate of the reaction, the slope of the graph, it shallows, or it becomes less over time, because as the NO2 is used up, the rate of the forward reaction will slow down. The rate depends on the concentration. So let's introduce rate laws here. Reactions are actually reversible, and we are going to see that in our next chapter as we start equilibrium. But we would rather, for the sake of this discussion, only consider the forward rate, or the rate in one direction. And this would be feasible if you started with only reactant. If you start with only reactant, you don't have a reverse reaction because you have no product to react in reverse. So if we talk about the reactions as being early on in the process, and for starting with only reactant, then it's quite feasible that we could talk about only the forward rate affecting the reaction. We find the reaction rate depends on the concentration, but the way it depends on the concentration can vary. Typically, we write the rate law. We call this the rate law, the rate equation, to be rate equals K, something we call the rate constant, times the concentration of the reactant, or reactants, in this case just the reactant NO2, raised to a power of N. In this case, N is the power of NO2's concentration. N is called the order of the reactant. We would say if N was 1, we would say that the reactant NO2 is first order. If it was 2, it would be second order. These orders can be integers, including 0. It's possible the rate will not depend on the concentration of one or more of the reactants. And occasionally, in some complex examples, we even find them to be fractions. So keep an open mind about what N could possibly be. The rate constants, which generally determine whether reaction is slow or fast. If K is a small number, the rate will be slow. If K is a large number, the rate will be fast. K is called the rate constant, and N is the rate order, and these two are going to be determined by experiment. So generally, we do not calculate K and N except from experimental data. The rate law is called, as it's formatted above, rate equals K NO2 to the N power. That is a form of the rate law that's called the differential rate law. What the differential rate law shows is how the rate depends on concentration. There is a second type of rate law called the integrated rate law. Some of you have possibly seen a connection between kinetics and calculus here, differentials and integration and all that. But the other type of rate law is called the integrated rate law, and it would show how the concentration of reactants or products depended on time. So in other words, maybe at a given time you could calculate the amount of a reactant or product from an integrated rate law. So we have some equations that give the rate as a function of concentration, and others that give the concentration as a function of time. Rate as a function of concentration is called the differential rate law. Concentration as a function of time, though, is called the integrated rate law. Now, how we're going to determine these rate laws depend primarily on experimental convenience. Let's say you had something that was aqueous and had a color. Well, you can measure that with spectrophotometry. Maybe you have a gas that is produced or used up. In the case of this reaction we're talking about, NO2 is a gas, and NO is a gas, and O2 is a gas. Well, maybe those gases could be collected and their pressures could be measured, or their volumes could be measured as a function of time. So that might be a better way to measure the rate law for a gas a, a gas reaction, or a reaction that involves gases. One other thing that I should point out here is that knowing a rate law can help us determine the steps of a reaction. Reactions typically have multiple steps, and those can be speculated on and theorized on if you know the rate law. We call the steps of a reaction a mechanism. We'll talk later in the chapter 12 about mechanisms. Finally, 12.3, how do we determine the form of the rate law? Well, the first thing you would want to find is the order of the reaction. In other words, that N value. Is it first order? Is it second order? Is it zero order? Is it half order? One way to do that is by the method of initial rates. With initial rates, what you do is you start your reaction with a certain known amount of reactants, and you measure the rate immediately after the beginning of the reaction, when the rate is based on the initial concentration that you added of the reactants. What you can do then is you can do multiple experiments with different initial concentrations and look at the initial rate as a function of those different concentrations. With this method, it's very typical to double one of the reactants and test to see whether the rate doubles or not. If you double the reactant and the rate doubles, it means the power or the order with respect to the reactant is first order, because doubling the reactant doubled the rate. If doubling the reactant quadruples the rate, then the reactant is to the second order. If doubling the reactant has no effect on the rate, it means the reactant is zero order, and so on. We have some data below for a reaction between ammonium and nitrite to produce nitrogen gas and water. This would be a reaction that could be easily monitored. One way to do it would be looking at the electrical conductivity of the solution. Ammonium and nitrate would be ions, nitrogen and water would be molecules, and so as this reaction proceeds, the conductivity of the solution would go down. Another way to measure this reaction would be the production of nitrogen. Regardless of how we measure the rate, let's say we could measure the rate in units of molarity per second. We would have 3 different initial rates for 3 different initial concentrations of ammonium and nitrate shown below. If we begin to analyze this, we compare experiment 1 to experiment 2. And for those 2 experiments, the concentration of ammonium is constant, 0.1 molar and 0.1 molar. The concentration of nitrite from experiment 1 to 2 doubles. It goes from 0.005 to 0.01. So ammonium is kept constant, but nitrite is doubled. Looking at the initial rate, it appears that the initial rate doubles from 1.35 times 10 to the minus 7 molar per second to 2.7 times 10 to the minus 7. So in that case, doubling the nitrite doubles the rate, so nitrite must be first order. If we compare experiment 2 to 3, from 2 to 3, we keep the nitrite constant at 0.01 molar, but we double the ammonium from 0.1 to 0.2. Now we see from experiment 2 to 3 that the rate again doubles. 2.70 goes to 5.40 times 10 to the minus 7 molarity per second. So it appears that doubling ammonium doubles the rate. So that must mean ammonium is also first order. So we would say that the rate equals the rate constant K times the concentration of ammonium times the concentration of nitrite, both to the first order. We would say the order of the reaction with respect to ammonium is first order. The order of the reaction with respect to nitrite is first order. We could also say that the overall order of this reaction is second order. So we're describing the kinetics of this. Now we could take any one of the experiments and plug them in, plug their information into this rate law, rate equals K ammonium times nitrite rather, and use the information in the data table to solve for the K value, the rate constant. Using any of the three experiments, the rate constant K would come out to be 2.70 times 10 to the minus 4 liters per mole per second. Again, excuse me. Now, why would we have these units liters per mole per second? Well, the rate would be in moles per liter per second, but we're dividing the rate by the moles per liter twice. So we have moles per liter divided by moles per liter squared. And that means we have moles per liter to the -1, which means we have liters over moles per second. So you can work it out with the units using this equation here and show yourself that the units would come out to be liters per mole per second, and that the numerical value of K would come out to be 2.7 times 10 to the minus 4. Once you get comfortable with this example, you could try another one, example 12.1 on page, in the section 12.3 in the textbook. So that concludes the first half of kinetics, and basically we're just looking at the way in which rate can depend on concentration, and how we write these rate laws for differential rate laws.